Okay, so remember what we were talking about? We were talking about cardinality. Right? Cardinality, right? So you have some function, right? You have some function, you have two sets, A and B. And you have some function going from one to the other. And remember that we say f is onto, right, or surjective. If what happens, right? If what happens, what does onto mean? What does onto mean?
Every element in B is hit by.
Right. Every element in B is hit by some element in A. Right. Right. So briefly, if the image of A is all of B, right? If the image of A is all of B, right? In other words, given any for all B in B, there exists some element in A such that f of A equals B, right? Given anybody in B, so it's a lot of notation, but I'm afraid you're going to have to get used to it. Given any element, given for all B and B, there exists an A in A such that f of A equals B. Okay. We say f is 1 to 1, 1 to 1, injective, if what? If what?
Each image only has one preimage.
Right, so if each, so the definition that Rudin has is like this. If for each B and B, the preimage of B has at most one element, right? There's at most one element in A that gets mapped onto it, right? So if I choose somebody over here, B, right, there's at most one guy over here that gets mapped onto it. Okay, I can't have two guys that get mapped to the same point. Okay, so what you want to keep in mind as your example is, I think, the squaring function that we had last time as our example from R to R, right? Right. So, and as we said last time, this example is it's actually a non-example, I guess, right? This example is this map is not surjective, right? It's not surjective because you don't cover all of R, right? You only get from 0 upwards, right? You only get from 0 upwards. It's not surjective, right? It's not injective, right? Because if I take a point here and if I take a point 1 and look at the pre-image, well, the pre-image is going to be -1 and 1, right? Both those guys get mapped to 1, right? And so in this example, right, the size of the pre-image of 1 is 2, right? And that's a problem, right? We don't. So it's not 1 to 1, right? So this map is not injective, right? It's not surjective. It's not injective. But if I change, yes.
Sorry, quick question. So when we talk about it not being surjective, doesn't that mean that we want to prove that there is at least one element in B which is not being hit by A?
Yeah.
But wouldn't that mean that, like, I'm confused because I thought that every element in B would be hit by A.
Well, like negative elements don't get hit by this thing, right? Because when I square something, I never get a negative.
Oh, because we have negative range as well.
Yeah, I never get a negative number. But you notice that if I restrict this a little bit, if I say I'm going to think of this function like f going from the positive, the non-negative reals to the non-negative reals. Okay, so I'm looking at the squaring function from like non-negative reals to non-negative reals, right? Well, that is onto, right? That is onto, and that is 1 to 1, right? Right. So this map actually is injective and surjective. Okay, and so it creates a one-to-one correspondence. So if you're both, right, if F is 1-to-1 and onto, we call it a one-to-one correspondence, aka bijective. We call it bijective. Okay, both injective and surjective, right? Or a bijection, right? So this map is a bijection. Okay. And we say that the cardinality. We say that the cardinality of A equals the cardinality of B. More briefly, the cardinality of A equals the cardinality of B. Right? Yeah, right.
Can you go over what a proper subset is real quick?
Proper just means contained in and not the whole set.
Okay.
So like A is a proper subset of B. Right? So it's a subset, not the whole set.
Yeah.
Okay. Okay. So, okay, everybody all right? Okay. I'm afraid that for the next, there's a lot of definitions at this point. That will sort of ease up later on, but for now we've got a whole lot of sort of very small definitions. Later on we'll hit more deep definitions and we'll have to deal with them. We'll have to expand them more. But right now there's just a whole lot of small definitions. Okay. Yeah. So one thing I wanted to say was that another way of saying one-to-one is that say it over here. Remark: F being one-to-one is equivalent to the statement if x1 and x2 are different, then f of x1 and f of x2 are different. Okay, so if you start off with two different things, you end up with two different outputs. Okay, you never have two different outputs ending up with the same output. Two different inputs ending up with the same output. Okay, so this is another way, a more common way of phrasing what one-to-one means. Okay, so then there are these terms, finite, countable, uncountable. Okay, you've read them. Tell me what they are. What does finite mean? Thanks.
There's an n in the positive integers such that you can map every element of the set from like 1 to n.
Okay. Okay. Yeah. So yeah. So we have some set. We have some set 1 to n. The numbers from 1 to n, and so if there exists. So let me introduce a notation. So notation that we did before, right? A total B will mean that there exists a one-to-one. There exists a bijection between A and B. In other words, that the cardinality of A equals the cardinality of B. Okay. Okay. So if A is equivalent to some J sub n, right? If for some n in the natural numbers, a set is equivalent to J sub n, we call a finite. We call a finite, right? So, it's so like your usual notion of what finite means. There's going to be n elements in it, right? Where n is some natural number. Okay. We let J denote the natural numbers. 1, 2, 3, blah, blah, blah. If A is equivalent to J, we call a countable. We call a countable. Okay. So, for example, right, if we look at the integers, 0, 1, negative 1, 2, negative 2, 3, negative 3, etc., right? Here are your integers, right? Then we can make a one-to-one correspondence with that and J, right? J is 1, 2, 3, 4, 5, blah, blah, blah. And so we can make a one-to-one correspondence between the integers and J, right? And so the integers are countable. Helen, are you okay? You okay, good. Yes, Susan.
What's the difference between J sub n and J?
J doesn't end. J doesn't stop. It's all natural numbers. J sub n stops at the nth term. So like J5 is 1, 2, 3, 4, 5. That's the end. So countable or countably infinite. Countably infinite. 3. If A is finite or countable, then we call A at most countable. And otherwise, we call A uncountable. Uncountable or uncountably infinite. Okay. Okay. So, you okay? All right. Okay. So, yeah, otherwise. Otherwise, which I always abbreviate O over W. Otherwise, we call A uncountable or uncountably infinite. Okay, and okay, so more definitions. Sorry, I'm trying to think of some way to make it more lively, but but I failed. So it's just more definitions. So any function from J into a set is called a sequence in A. A sequence in A, right? So, J is J we call it 1, 2, 3, 4, 5, blah, 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 right? And you have some function A into a set, right? You have some function from A into a set, right? So you've got A of 1 A of 2, right, A of 3, et cetera, et cetera. So you've got this infinite sequence of points, right? So this kind of function is called a sequence, right? And you're well aware from Calc 2, I guess, that you normally call this thing a sub 1, a sub 2, a sub 3. So for sequences, you don't use the function notation, you just use the subscript notation. So that's pretty common. Okay, and
Professor,
Yeah.
like a weird question.
Yeah, go
It
ahead.
relates to like the sets that we declared for the definitions. So like in the textbook it mentioned that for finite sets it is if it's bijective to the j with the n numbers, but it is also said the empty sets also considered to be finite, but it
Mm-hmm.
goes until n. So in this it considers 0 is positive.
oh,
Number?
yeah. So,
How does that work?
yeah, that's true. So by this definition, by what we've just written up here, then the empty set, isn't finite, right? But we still call it the empty set finite, okay? Because it sort of satisfies what you would want to think of as finite. Okay. So, yeah. So maybe say it this way: for non-empty sets, if it's equivalent to some j sub n, we call it finite. For the empty set, we just call it finite.
How do you kind of determine that it's finite?
Well, it's just the number of elements it has. How many elements does the empty set have? 0, right? Well, 0 is a finite number. So you definitely want to call the empty set finite. It's not an infinite set, right? There's not infinitely many points in it. In fact, there are no points in it.
But that's with the assumption that there are no repeats. So there could be set that contains like many zeros, for instance.
We're not. That's just when you're talking about a set, you don't count repeats, right? As a set, you don't include repeat elements, right? Right. I don't say like I don't call the integers as saying 0 and also 0 and also 0, right? You as a set, it's just there are these elements. There's 0, 1, -1, blah blah blah, right? Okay. So just one remark. If you have any one-to-one onto a sequence, right? Any one-to-one onto sequence from, in other words, from J to A, gives a one-to-one correspondence from A to J. Right. So if I have a one-to-one sequence, I know that my set is equivalent to the natural numbers.
Wait, so how do we know it's equivalent to natural numbers? How do we know that the property of J or N is?
Sorry, J is the natural numbers. Right?
Okay.
J is the natural numbers.
Awesome, yeah.
Maybe I should have just used N instead of J. Okay. So the point is this: that if you have a sequence, if you have a one-to-one onto sequence, well, that gives you a correspondence between A and the natural numbers, right? And vice versa, if you have a correspondence between A and the natural numbers, well, that gives you a sequence, right? Because if I have some correspondence 1, 2, 3, 4, 5 with all the elements of A, well, then that gives me a sequence, right? That will give me a sequence. So, Okay, so now let's prove some theorems. So theorem number 1, every infinite subset of a countable set is countable. Every infinite subset of a countable set is countable. Okay. Right, so okay, so so here's proof. So say that E is a countable set. No, say that A is a countable set, and that E is infinite. Suppose you have some countable set, and suppose you have some infinite subset of it. Okay. So what we want to do is just create a yes.
Does it mean that A is also infinite?
Yeah, because remember what countable means. Countable means equivalent to the natural numbers, right? So it's going to be infinite. Okay, so right, we want to show that this E is countable. We want to show that this E is countable. So what does that mean? We want to make a sequence onto E, right? We want to make a sequence whose image is E. Okay. So you say, okay, well, we know that A is countable, so can be arranged in a sequence. In a sequence, x1, x2, x3, x3, right? Yeah, Howard.
Why can you make that conclusion? Like because A is countable, you can arrange it into sequence?
Okay, so this is what I was trying to say over here, and I think I didn't say it clearly enough. So what does countable mean? Countable means that there's a one-to-one correspondence between your set and the natural numbers, right? So you know that there's some function going from the natural numbers to A, and this is a one-to-one and onto function, right? So what are the elements of A? Well, they're going to be f of 1, f of 2, f of 3, f of 4, right? And since it's onto, I'm going to hit every single element of A. If I look at this sequence of points, I'm going to hit every single guy in A, right? And since it's one-to-one, I'm going to hit each of them once, right? I'm never going to get them once. Okay. So, having your one-to-one correspondence means basically that you can put your set in a sequence. Okay. Does that make sense? Okay. So right. So being countable means there's a one-to-one correspondence with n. Well, having a one-to-one correspondence with n means that you can be arranged in a sequence, in a list. Yeah.
So being countable is equivalent to being a bijective sequence. Is that one-to-one onto sequence? Is that?
Yeah.
Okay.
Okay. Okay. So A is countable, so you can arrange it in a sequence, right? And we're trying to show that E is countable. In other words, that E could be arranged in a sequence. Okay. Well, you say, okay, well, what are we going to use? What are we going to do? We say, well, let n's of 1 denote the first integer such that x of n's of 1 is in E. Right? So you just go down the list and you say, okay, this guy is in E. Well, let's call that guy, let's call its index n sub 1. Okay. Right. Let n sub 2 be the second index. Such that x of n sub 2 is in E, and so on and so forth. Right? Right? And so then let E sub I be defined as x of n sub I for all I, for all I equals 1, 2, 3, etc. This E sub I is a sequence describing all elements of E. Right? This thing gives you all elements of E, and it hits each of them only one time. Right? So E is countable. Right? You found a one-to-one sequence. Right? You put E into a list. Okay, talk to each other for a minute and see if you have any questions.
We don't have to prove for a finite subset or a countable subset. Shouldn't be countable. Do we have to prove for a finite subset of a countable set?
Well, we're talking about.
Yeah, because for a finite subset, it's always going to be countable.
So remember, countable means infinite, actually, right?
We have A is finite, we call A countable.
We call it at most, so it's called at most countable. That's different from countable.
Okay, what does this?
It's countably infinite.
You can count it, you just don't choose finite or infinite.
So you have 1, 2, 3, 4, 5, but it's all, it can be all the way to infinity. That's countably.
These words seem the same.
It's finite, you can definitely count it, right?
Yeah, but.
So then you don't count it countable, you just call it finite.
Sorry?
That is countable, you just don't call it countable.
Yes. It's countable and or
You're using English counting, math counting. English counting means I can count.
But it must be in math.
E1 is and 1, which was the first guy in E.
Okay.
E2 is E and sub 2, which is the second guy in E, and so on and so forth. So this is the function.
So Professor, is
Yeah.
it fair to say that because we put the elements of the into a sequence, we
Yeah.
found a one-to-one correspondence between the natural numbers and
Yeah,
which is why we can say it's countable.
exactly. Yeah. Yeah, so this is actually, and vice versa, right? It's, if you have a sequence, then you get a one-to-one correspondence. If you have a one-to-one correspondence, you have a sequence, right? So, maybe I should say it like this. This is equivalent to that, right? The existence of a one-to-one on the sequence is equivalent to the existence of a one-to-one correspondence. Yeah,
But like sets aren't ordered, so is like the E sub I like some sort of like arbitrary or?
I'm not following. We're not worrying if the set is ordered or not, right? What we need is a one-to-one correspondence from the natural numbers onto E, right? And we create it, right? I guess you could say that puts an order on E, but that's not relevant to the statement. Other questions? Okay, yeah, Mitchell.
Yeah, so
Yeah.
what properties do a finite or countable set share? Because the book said we call a set that is finite or countable at most countable.
Mhm.
So that like when we each start a proof and we say that something's at most countable, it means it's going to share certain properties. Or
Well, I mean, it just means that it's either finite or countable,
okay.
right? So, this is sort of too wide a question.
So what can we do with an uncountable set that we can't do within a most countable set?
Oh, count them. No. It's just, I mean, you're all laughing, but this is actually the real answer. If I say, I create a sequence, A1, A2, A3, blah, 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 right? And I know that my set is uncountable. Well, I'm never going to cover that set, right? I'm never going to cover all elements of. I can't say, oh, this is equal to the whole thing, right? I can't say this infinite set of points is this set because this is countable and this is uncountable.
Sure.
Right? I'm never going to reach everybody. Okay. If this thing is countable or finite, then I say, okay, I know I can put it into a list.
Sure.
Right. So I can put it into some list, either an infinite list or a finite list.
Okay.
Right. So that's the point. Yes.
Yeah, is that this so that at the end we will show that the real numbers are not countable?
Yeah. So later on,
Okay.
very soon, we'll
That's
see.
the end game. Okay.
Real.
So yeah.
Well, yeah.
Okay. So this is basically defining two kinds of infinity. Okay. There are two kinds of infinity, right? There's the cardinality, right? Some things can be given the same. You notice that they have the same cardinality as the natural numbers, right? And maybe some things have the same cardinality as the real numbers, right? Those are both infinite, but you cannot put the real numbers in a one-to-one correspondence with the natural numbers, right? These are actually different cardinalities, right? Okay. So. Okay. Well, let's. I think people are getting it. I hope people are getting it. Okay. So just some notation that I hope you're already familiar with. So set notation. Set notation. You have some set omega a set. Okay. And you have alpha another set. Okay. This omega you want to think is the space that your other sets are in. Okay. So you have, you also have, for each A in A, you have a set E sub A in omega. Okay. So this A is your index set. Really, this is your set of indices. For example, the numbers, right? The natural numbers, right? And this omega you want to think of as your ambient space, right? Your subset, right? So your E sub A's live inside of omega, right? For example, to make it concrete, right? You could say that omega is R2. Right, and A is the natural numbers, right? 1, 2, 3, blah blah, and then maybe for each E sub I, you have the ball, the disk, radius I, centered at the origin. Centered at the origin. Okay, so that these guys live inside of omega, right? They live inside of R2, and they're each one is associated with one of these indices. Okay, so that apparently was confusing to some people, right? So you have a bunch of sets that live inside some space. Okay. 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 Now, so basic notation, right? If I write E sub alpha in A, right? The union of the E sub alpha, the union of all E sub alpha. Well, that's going to be the points, any points such that x lies in some E sub alpha, right? For some alpha, right? Right? The union is going to be means that you could lie in any one of the any one of these sets, right? So, right, if I have a bunch of sets, well, the union means all you need to satisfy is that you lie in one of these sets, right? You lie in some fixed set. Okay. The intersection, of course, is the intersection is, what should I write? X is in omega such that what?
It's in every E sub.
You lie in every E sub alpha. Right? X lies in the alpha for all alpha. Right? So you have to lie in all the alphas, all the E sub alphas. Okay. Okay. So some basic rules of sets. Basic rules. So these do need to be proven, but I'm just going to state them. So A is contained in the union, right? So any set A is contained in the union of A with something else. The intersection of A with something is contained in A. A union intersection, A union, the empty set is A intersect, the empty set is the empty set. For if A is contained in B, then A union B is B, right? And A intersect B is A. Right? And okay, anyway, there's some more. They're in the book. You can read them. There's no point in me writing them again. Okay. Okay. So let's combine this sort of thing with countability. So here's the theorem. Let E sub n from n equals 1 to infinity be a sequence of countable sets. Okay. So you have an infinite sequence of countable sets. Right? You have an infinite sequence of countable sets. Okay. Then the union of all those guys, infinity is also countable. Then the union is going to be countable. Okay, so a countable union of countable sets is countable in English. A countable union of countable sets is countable. Okay. Okay. So here's the proof. You say, okay, take each E sub n, right? Each E sub n is countable. So arrange each in a sequence. Right? Arrange each in a sequence. So E sub n can be put into a sequence, x of n1, x of n2, x of n3, et cetera, right? It's countable, right? So we know that there exists a bijection from n to E sub n. Well, this bijection from n to E sub n is a sequence, right? So use that sequence and write it down. Okay. So now consider all the terms, x11, x12, x13, x14, etc., x21, x22, x23, x24, etc., x23, x31, x32, x33, etc., So you put down, right? You put down all the terms, right? And say, okay, well, the union. Let me denote this thing by S. The union S is all these terms here. Okay. So I just start. I make a list of all the terms, right? I make a sequence by just winding around, right? I go like this, come back, right? Like this. And I keep on going like this, right? I make a long list. This is my first term, my second, my third, right? My third, fourth, fifth, sixth, etc., etc. Just wind back and forth, right? And so what you've done is you've made thus S S can be arranged in a sequence, right? In a sequence, right? x11, x12, x21, etc. With possibly duplicates. Right? So it might have, some of these terms might be the same, right? Even though in each row all the terms are different, right? We don't know that there might be some duplication between rows, right? Maybe this guy and this guy are the same term. Okay. Maybe these guys are the same elements. Okay. So you have this sequence, but it might have some duplicates. Okay, but in any case, S is thus equivalent to some subset T of the natural numbers. Right? Right? If we toss out the duplicate guys, well then we have a one-to-one correspondence. Right? Toss out the duplicates, that gives you a one-to-one correspondence between S and some subset of the natural numbers. Right? You've thrown out some of the indices, so maybe you lost some of the numbers. Okay. 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 So Okay. Since E1 is contained in S, since E1 is contained in S, and E1 is infinite, you know that that T is not finite. Right? That set of indices couldn't be finite. Right? That set of indices couldn't be finite because the E1s were all different, right? So the T is not finite, right? And so, right? So T is an infinite subset of a countable set. And right, it's an infinite subset of n, right? And so by the previous theorem, T is countable. Right? T is countable. S is equivalent to that countable set, so S is countable also. Yeah, Edward.
Are we trying to establish an injection between S and N? Can we say that?
Yeah.
So whenever we have an injection between a set and N, that set is countable. Is that statement true?
Well, it could be finite.
It could be finite.
Yeah.
Once
So it's either finite or
once it's
infinite.
infinite, then we can say so.
Exactly. So we needed to show that. Yeah. Okay. Any questions about that? Yes.
Is there an example of an uncountable union?
Of an uncountable union? Sure. So you could have some sets which are indexed with real numbers. So like R is a real number, right? So you've got sets each corresponding to some real number, but that would be an uncountable union. Yeah. Okay, that's it for today.